So D and F block elements. So first let us see its introduction. So D block elements are means these are the elements which have there is a feeling of D block, means electron enter into yes, and penultimate D subshell, n minus 1 D subshell. Nth shell is called valence shell, n minus 1 is called penultimate shell, and n minus 2 antepenultimate. So the element in which differentiate electron enters in the penultimate shell, they are called D block elements. So where can you find these elements? So this is the yes. So this in the extreme right there is a P block. In the middle there is a D block, and in the extreme left there are S block elements. S block elements are highly electropositive. P block elements are highly electronegative. So D block elements show the transition from most electropositive elements to most electronegative elements. So D block elements, these are the D block elements. So इसको याद करने का आप ऐसे कर सकते हो, इसको याद है आपको एलिमेंट्स? ओके तो डी ब्लॉक एलिमेंट्स में ये जो 119 है दैट इज डिस्प्रोसियम टर्म स्टेडियम सॉरी, and next one is orangeinium, and other one is copernicium. So these are 110, 11 and 12. So D block में there are 3D, 4D and 5D series. So in 3D, 4D, 5D and 6D, starting elements are scandium, yttrium, lanthanum and actinium. Yes. And these are in the group 3B. Or we can say group 3. Ending elements are zinc, cadmium, mercury and copernicium. And that is group 12 or 2B. So group number we can determine scandium is which आपके speaker on है, it is 4s2 3d 1. Then 5s2 3d1. Turn off your speaker please. Hello. Actinium still hello. Yes. Now is it okay? So zinc, cadmium, mercury and copernicium, it is 4s2 3d10, 4s 5s2 4d10, 6s2 5d10, 7s2 6d10. So group number is equal to number of ns electrons plus number of n minus 1 d electrons. So scandium, yttrium, lanthanum and actinium, they are first members. Zinc, cadmium, mercury and copernicium are the last members of the D block series. So general electronic configuration is n minus 1 d 1 to 10 and ns 1 to 2. It is ns 1 to 2, n minus 1 d 1 to 10. Sometime it can be written as ns 0 to 2 to include palladium, because palladium is the element where electronic configuration is, yes. So this is general electronic configuration ns 1 to 2, n minus 1 d 1 to 10. So go 3D series क्यों बोलते हैं? Because last electron enters in 3D. Yes. और general electronic configuration of 3D series is 4s 1 to 2, 3D 1 to 10. So in 4D, you know, it is 5s 1 to 2, 4D 1 to 10. Then 5D, so it is 5s 1 to 2, 4D 1 to 10, 5D series 6s 1 to 2, 5D 1 to 10. Last is 7s 1 to 2, 6D 1 to 10. Scandium का और Sc2 Si2O7 means it is a silicate. Then titanium, it is FeTiO3. Vanadium Pb5 VO4 thrice Cl. Chromium, this is most important. It is used in, where it is used? No. No, I am talking about this ore. बाद में बात करता हूँ. Fe, it is used as a starting material for the preparation of potassium dichromate, chromite ore, FeO.Cr2O3. That is most important. Maybe like a matching type question. But this FeO.Cr2O3 is most common, reason being it is used as a starting material for the preparation of potassium dichromate. In case of manganese, MnO2 is most common. That is called pyrrolysite ore. And it is a starting material for the preparation of potassium permanganate. Iron hematite, magnetite, cobalt is not very important, but this copper cuprite, Cu2O, this malachite, CuC, means it is basic copper carbonate, CuCO3, CuOH twice. Azurite is there's difference of in 2 moles of CuCO3 with 1 mole of CuOH twice, that is called azurite. Nickel zinc blend, that is important. Zinc carbonate, calamine. It is zinc is also found in the ores of silver, copper, lead and platinum.
Yes.
Copper exists as Cu. Nickel exists along with cobalt, ores, nickel, cobalt. So first general characteristics of transition element is they form complexes. Why they form complexes?
Because of their ability to accept electrons.
Because they have vacant d orbital, means partially filled d orbital, and they can have variable oxidation states.
Yes.
They have high melting and boiling point. Why?
Due to this
Because they have large number of unpaired electron.
Yes.
So they can form strong metallic bonding. In most of the cations of transition elements, they have unpaired electrons.
Yes.
They show high density, malleability, ductility. They possess metallic luster. They are good conductors of heat and electricity. Why except zinc, cadmium, mercury and copernicium? Very good, because they have no unpaired electron as such.
Yes.
They form in organometallic compounds. What are organometallic compounds? Which have carbon metal bonds. They have a strong metallic bond. Same reason, because they have large number of unpaired electrons. That's why they have strong metallic bond. Because they have strong metallic bond, that's why they have high melting and boiling point. They possess catalytic properties. Again, same reason, because they provide surface for the reaction to take place. They have vacant orbitals, they can form complexes. They have variable oxidation state, so they can form various intermediates.
Yes.
If we have 1 kg of cotton and 1 kg of, so obviously weight of, but density of volume is of this iron piece is less, so that's why iron has high density. So density of D block element is high, and they are denser than even S block elements.
Yes.
Because S block elements are large in size. So solid, liquid and gas, if we compare, atoms of solids are closely packed, and if we convert into liquid, they have now high energy.
Yes.
If we convert liquid, means solid into liquid with ease, that means they have low melting point. If it is difficult to convert, that means they have high melting point. So it all depends upon the interatomic strength.
Yes.
If we compare melting point with atomic number, see, first it increases up to chromium, then there is a dip, and then further there is an increase, and then it decreases. Why is it so?
So because somewhere between they are having no unpaired electrons.
Because first there is an increase in number of electrons, unpaired electrons.
Yes.
Then for manganese and technetium, they have large number of unpaired electrons, but melting point decreases. Why is it so? Because see, when we have manganese, it has exactly half-filled configuration, 3d5 4s2, technetium 4d5 5s2, means they have extra stability, and therefore the electrons are less willing to participate in bonding. Okay, that's why manganese, there is a dip for manganese and technetium, and as we go down the group, melting and boiling point increases because electrons are more freely available for bonding. So what we observe, we see the melting point initially goes on increasing and then
Yes.
decreasing steadily. So reason for this behavior is up to D5 configuration, number of electrons go on increasing, and number of electrons, unpaired electrons, also go on increasing. So metallic bonding becomes stronger, and therefore melting point increases. But after that, pairing starts.
Yes.
So number of unpaired electrons decreases. Now ionization potential of D and F elements. So what is ionization potential? How much energy is required to, yes, to remove the electron and to make it cation. So energy required to form cation, that is called ionization enthalpy. In an isolated gaseous atom, that's, you know. So when we go from left to right, what happened to atomic size? It decreases. So as atomics, sorry?
From left to right, it will decrease, sir.
Yes. That's what it is. It decreases. So ideally, there should be increase in ionization enthalpy because size decreases. So electrons are tightly held by the nucleus. At the same time, nuclear charge also increases. But if you see the data, you can see that, see, first it slightly decreases, then it increases to the top, then decreases, and at the end it increases. Same for next second transition series, see there is a so much of variation. So for palladium you can explain easily. See again there is a change, means it is not as smooth as we can expect. So it is observed that first ion enthalpy increases, but increase is not very regular, you can see.
Yes.
Because added electron enters in case of last last series, that hafnium, tantalum, tungsten, added electron enters F block, due to which shielding is extremely poor towards the valence electrons from the nucleus, and therefore ion enthalpy of third transition series is more than first and second.
Understood.
So we can predict thermodynamic stability of metal compounds, like this is the best example, nickel and platinum. So if you see the first two ionization enthalpies, the first two ionization enthalpies of nickel is less than platinum. So that means nickel compounds are more stable in +2 oxidation state. But if you see the sum of the first 4 ionization enthalpies, you can see the sum of the first 4 ion enthalpies of nickel is more than that of platinum. So sum of the first and second enthalpies of nickel is less. So that means nickel 2+ is more stable than platinum 2+.
Yes.
But sum of the first 4 ion enthalpies is less in the case of platinum. So it indicating platinum 4+ to be more stable than nickel 4+. So it can be used in calculating energy of the system, in calculating heat change. So first ion enthalpy increases, but increases not very regular in D block. What is the reason? So it is because of poor shielding. And at the same time, exceptional electronic configuration, that is also the reason. It is observed that first ion enthalpy of 5D series is quite high.
Because of the 5D series. It starts showing lambda. Okay, it shows actinic contraction, right?
Last series is hafnium.
Yes, sir.
It should be option B, but by mistake it is written here. It is because of actinic contraction, because there are electrons in the 4F field,
Yes, sir.
and therefore that will enhance its ionization enthalpy. Ionization enthalpy is useful in calculating all of them.
Yes, sir.
Why nickel 2 plus found to be more stable than platinum 2 plus?
Option C, sir.
It's because sum of the first and second ion enthalpy is less in case of nickel. Now oxidation states and atomic radii. So oxidation state is the net numerical change present on an atom of an element in a molecule is known as oxidation state. So atomic size, if we go from left to right, atomic size decreases. Oxidation state should ideally go on increasing, but see, scandium it is +2 +3, titanium it is +2 +3 +4, vanadium it is up to +5, chromium it is up to +6, manganese it is up to +7. So it is increasing up to manganese. Then for iron it is generally +2 and +3, and it can also show +4 +5 and +6 in some of the compounds. So see, now there is a decrease, and zinc can show only +2. So this is the, so which one is the most common? The highest, most common is +3 for scandium, +4 +5 +6 +3 and +7, +2 +3 for iron and cobalt, +2 for nickel, +1 for copper, even +2 is most common. Zinc is only +2. So oxidation states are variable. The reason is there is a small energy gap between Ns and N-1d subshells, and therefore both can participate in bond formation. So energy gap between 4s and 3d is very small. But in case of 1s and 2s, it is very large.
Okay.
So that's why number of electrons goes on increasing. So oxidation state also goes on increasing. And maximum oxidation state of 3D series is +7. Yes. Because number of electrons, unpaired electrons, go on increasing up to manganese. And therefore, again, in the next case, there is a pairing of electrons. So number of electrons decreases. And that's why electrons are more tightly attached to the nucleus, so difficult to remove. So can we deduce a formula for minimum and maximum? Minimum is number of electrons in Ns subshell, and maximum oxidation state is number of unpaired electrons in D subshell plus number of electrons in Ns S subshell.
Okay. This can be used for all elements.
Not for all. It is up to when electron pairing does not take place.
All right.
So see, in case of 3D series, first atomic size decreases, and see, iron, manganese, iron, cobalt, nickel, copper, they have almost same size, even chromium, and at the end it increases.
Yes, sir.
So this is the scenario. So see, initially atomic size decrease is large.
Yes.
So initially atomic size decreases because nuclear charge is dominating. But as number of electrons are filled and there is the inter-electronic repulsion when pairing starts, then what happened? Inter-electron repulsion is dominating, and in between there is a balance between nuclear charge and inter-electronic repulsion.
Yes.
Because if inter-electron repulsion is large, electron cloud expands, so size increases, means inter-electron repulsion is in favor of size,
Understood.
increase in size, but nuclear charge contracts electron cloud. So initially nuclear charge is dominating, and at the end inter-electron repulsion is dominating.
Understood.
So see, first it decreases because nuclear charge is dominating, and then it remains constant because nuclear charge and screening effect that balance each other. Inter-electron repulsion is directly proportional to screening effect. So finally it increases because repulsive forces of the added electrons increases, and therefore orbital starts to expand.
All right.
Which of the following does not show variable oxidation state? A valency? Yes, zinc has only +2. Atomic size increases towards the end of the transition series. What is the reason? Because of repulsive forces. Most common oxidation state shown by plus 3D series is +2. Which elements have abnormal configuration? It is obviously chromium and copper.
Okay, +1 is
3D1, 4s1, 3D5, 4s1, 3D10.
yes.
Atomic size of D block elements remains constant for some elements.
Okay, option A, sir.
So it is option A.
Okay.
Because of nuclear charge is balanced by screening effect. Now standard electrode potential. So if we see the trends in M2 plus M standard electrode potential, some of the enthalpies of sublimation and ionization, it is not balanced by hydration enthalpy in case of copper. That's why electrode potential of M2 plus copper 2 plus copper is positive. Only one element in 3D series have positive reduction potential, and so And due to this positive standard reduction potential, it cannot liberate hydrogen gas from acids.
Yes.
So see, only copper is above 0. So values of standard reduction potential for manganese and zinc are more negative than expected. It is because of stability of half filled in case of manganese and completely filled in case of zinc 2+.
Understood.
Standard electrode potential you can see. So see, first minus 1.63 and then it decreases, means it becomes less means overall it increases, becomes less negative up to chromium, and then there is again dip. See, it becomes minus 1.18 in case of M3 plus to M2 plus, it becomes positive, that is plus 1.57. Same reason, because M2 plus has exactly half filled configuration. Same you can see for zinc. It is minus, first see minus 1.18, then minus 0.44, it increases up to copper, and then there is a fall again due to
Then will I be able to estimate the trends?
yes, we can, but there are other factors as well. There are other factors, like if it is one of the criteria, ionization enthalpy, then there is sublimation enthalpy, then there is hydration enthalpy. If we know the data, then we can predict. No. So scandium has low value. Why? Because scandium 3 plus has noble gas configuration. So scandium 3 plus is reluctant to convert into scandium 2 plus. For zinc, it is highest, because if we remove electron from zinc 2 plus, or if we add electron in zinc 3 plus, it becomes more stable, D10 configuration. Comparatively high value for manganese, because Mn2 plus is particularly stable. Iron 3 plus has extra stability, so it has low value.
Yes.
So highest numbers are achieved in titanium halides, VF5, CRF6. So ability of fluorine to stabilize highest oxygen state is due to either higher lattice enthalpy or high bond enthalpy. For example, VF5 and CRF6. So In +1 there is only copper. Now another feature of fluoride is their unstability in the low oxidation state. They are not stable in low oxidation state because fluorine is strong oxidizing agent. So it can oxidize elements in higher oxidation state, and because of its small size, they can be accommodated more around the metal. Like see Cu2 plus, that oxidizes iodide to I2. So Cu2 plus is converted to Cu1 plus, Cu2 I2. So copper 1 compounds are unstable in aqueous solution and they undergo disproportionation. So stability of copper 2 plus rather than copper 1 plus, it is due to much more negative hydrogen enthalpy of copper 2 plus than copper 1 plus, and it is more than, it is compensated by second ion enthalpy of copper. So in aqueous solution, hello, yes, in aqueous solution copper 2 plus is more stable than copper 1 plus. Now chemical reactivity and hydration enthalpy. So you know E0 values of M2 plus to M, there is a decreasing tendency to form divalent cations.
Yes.
It become less negative in E0 values. It is related to some of the first and second ionization enthalpies. मैग्नीज, निकल और जिंक के लिए इट इज मोर नेगेटिव देन एक्सपेक्टेड, तो बताया ही था, बिकॉज ऑफ एग्जैक्टली हाफ फील्ड कॉन्फ़िगरेशन और फुल्ली फील्ड कॉन्फ़िगरेशन विच हैव एक्स्ट्रा स्टेबिलिटी. It is true for manganese and zinc, and for nickel it is because of highest negative enthalpy of hydration. So वो आपको अलग से याद रखना पड़ेगा. So based on the E0 values for the redox couples, you know, Mn3 plus and cobalt 3 plus, they are strongest oxidizing agents in aqueous solutions. Titanium 2 plus, vanadium 2 plus, chromium 2 plus, they are strong reducing agents, and that's why they can liberate hydrogen from dilute acid. So see, chromium 2 plus is converted into chromium 3 plus, H plus into H2.
Yes.
दो आयरन बार लिए हमने of the same size and same density, and one is under the influence of magnetic field, other is, so obviously you know so which move, the substances which move towards magnetic field, they are paramagnetic, and the substances which move away from it are diamagnetic, and substances which are strongly attracted towards iron metal are called ferromagnet. So paramagnetism actually arises due to the presence of unpaired electrons, और उनमें मैग्नेटिक मोमेंट होता है, और वैल्यू वी काउंट ओनली स्पिन, सो इट इज अंडर रूट n into n plus 2 बोर मैग्नेटो. n is number of unpaired electrons. So in this way, unpaired electron के base पे you can calculate magnetic moment. So see, magnetic moment calculated is different from observed. What is the reason? But they are very close to each other. But why there is a variation in observing magnetic moment? Because of because of sorry, no, it is because of the contribution from orbital magnetic moment. Actually, under root n into n plus 2 is because of spin only magnetic moment. we are लिखते हैं ना, it is spin only magnetic moment. ठीक है, और इसका फॉर्मूला क्या होता है? अंडर रूट n इंटू n प्लस 2. And this is called spin only magnetic moment, right? Actual formula is this one. This is spin contribution, this is orbital contribution. Capital S is total spin, capital L is total magnetic moment, the angular momentum, है ना? So total, actually if we consider only, we neglect this part because it is very, very less. So we take into account this one only. So what is total spin? That is n by 2. N is number of unpaired electron. So 1 S means number of unpaired electron divided by 2. So it is 4 n by 2, n by 2 plus 1. So it comes out to be under root n into n plus 2, right? So this is actually spin only magnetic moment. So we neglect the orbital contribution. So if we consider both, then there is somewhat variation. So formula for calculating magnetic moment is under root n into n plus 2. Now color properties of transition elements. So color means, there are different colors. So color is observed. This is complementary to the color absorbed. So see, Vibgyor, in Vibgyor we say when it is violet and yellow are complementary to each other, blue and orange, green and red. So, but this theory, this Marshall wheel, this theory could not explain the existence of colors like pink, brown. So that's why it is ruled out. And next theory that came up, that is totally new concept. As we know, we have 5d orbitals.
Yes.
So one electron in 3D. So when electrons from other atoms or molecules approach these 5D orbitals, what happened? These split, that is CFT. So they split into two parts, that is called crystal field splitting. So they are T2G and EG.
Yes.
So now when the energy is supplied, what happened? This electron shift to EG level, and this is called DD transition. So higher energy, if there is a higher energy, then stability is lower. In order to attain stability, electrons in the higher energy level emits energy, and that comes back to the lower energy level, and energy is released. And this energy emitted, if its frequency matches with that of the color in the visible region, then we see color. It is not always true that it should be, but most of the DD transitions are in a visible region. But in case of F block elements, few of them are colored, others are colorless, because the FF transition that can be in a UV region.
Understood, sir.
So transition elements and their ions exhibit colors due to the presence of unpaired electrons and due to DD transition. And the color observed, that corresponds to the complementary color of the light absorbed. These ions, some of the oxo anion, this is the most common. MnO4 negative, CrO4 2 negative, Cr2O7 2 negative. They exhibit color due to charge transfer phenomena, and that charge is transferred from ligand to metal.
Yes, sir.
See, when there is D0, they are colorless. D1, D2, D3 up to D10, they are colored.
All right.
But when you see D10, it is again colorless.
Yes.
So which one is green in color? So it is nickel. Iron 3 plus says brownish, means yellow. Now formation of complex compounds and catalytic properties. So complex compounds are those in which metal atoms or ions, they bind to the number of anions or neutral molecules, and they give complex species with the characteristic property like FeCN6 3 negative, FeCN6 4 negative, CuNH3 4 2 positive, PtCl4 2 negative, now complex formation is due to comparatively smaller sizes,
Yes.
high ionic charges, then vacant d orbitals, now catalyst. Catalyst increase the rate of
Yeah.
reaction. So conditions required to behave like catalyst. So it is, first of all, p valence electron should be there, availability of vacant d orbitals, large surface area, variable oxidation states, and as a result their ability to adopt multiple oxidation states and to form complexes. So that is why they act as catalyst. So transition elements and their compounds are known for their catalytic activity, and this is referred to their ability to adopt multiple oxidation states and to form complexes. Example is vanadium oxide in contact process, finely divided iron in Haber's process, nickel in catalytic hydrogenation of oils. So palladium with barium sulfate, that is large catalyst that we have covered. Transition elements can change their oxidation states, so they become more effective as catalyst. Like iron 3 that catalyze this reaction, iodine and persulfate. So first of all, Fe3 plus ion convert I negative into I2 and Fe3 plus into Fe2 plus, then Fe2 plus ion that react with S2O8 persulfate to give sulfate. So why do we see color in the transition complexes?
Because of DD transition.
Because of all of them, because crystal field splitting, so then there is a transition, because if there is no medium, no solvent or no ligand at all, there is no DD transition.
Yes.
Splitting of d orbitals is called crystal field splitting.
Yes.
Catalyst increases, yes, rate of reaction and number of reactants that is reacting. That's why rate of what?
Do we count the catalyst as a reactant?
Because rate of reaction increases because of decrease in activation energy, right? But if reactants are given, because actually why rate of reaction increases? Because more reactant is converted into product.
Yes.
It is decrease in concentration of reactant versus time taken. So in which form solids are used? Finely divided powder, right? Now formation of interstitial compounds. So nothing is 100% pure. Even purest gold is 99.9% pure. So 0.1% is foreign atoms as impurities. So they are occupied in interstices. And compounds having foreign atom embedded in between, these are called interstitial compounds. So because of this, there is a we cannot represent the definite composition because they are somewhere in between, right? And there is no as such formula to calculate how many interstitial species are there, right? Because atoms are trapped, which are not too large or not too small, means they are nearly of the size of the void. Yes, steel is an interstitial species. So alloy, when atoms have almost same size, then there is a formation of alloy. And due to the similar sizes, atoms of one type can replace by other if there is a difference in size of plus minus 15%. So alloys are hard, like some boroids will approach diamond in hardness, even means harder than diamond. They have high melting point than that of pure elements. They retain metallic conductivity. They are chemically inert. It is true about interstitial compounds even. So difference is plus minus 15%. Okay. So preparation we will do in the evening. At what time you are free?
Between 7:30 and 9:80.
Okay, I will send a link at 7:30. Okay, beta. Bye. Bye, beta. Welcome.